So we've seen how with e-beam lithography we can quickly make a nanostructure, and then by following our exposure with etching and so on, have a device. But it's just one device. The focused ion beam removes the need for the etching, but even there we're writing the devices one at a time. How could we churn out millions of devices with nanoscale features? This is a problem addressed by Richard Feynman in his book There's Plenty of Room at the Bottom, and his lecture. And his suggestion was, let's go ahead and make some fine nanostructure on a surface by whatever difficult means we care to, and then let's pour over that some rubbery or liquid compound and then cross-link it so we get a rubber mold whose shape then corresponds to the inverse of the shape that we want to make. So now let's stamp out the structure using the rubber mold. Well, this scheme has been put into practice in the last few years using polydimethyl siloxane or silicone, which it turns out can mold itself conformally to nanometer scale molds that have been made using the lithography techniques I told you about earlier. Panel A shows a form of lithography in which the mold is used to stamp reactive chemicals onto a surface. So the mold is dipped into a pool of chemicals so that when it's pressed against the surface, the only place that the chemicals are deposited are the places where the high points on the mold. Now, in order for this to happen, the chemicals themselves can't diffuse around on the surface, so thiol here means that, for example, it could be a rather non-reactive chain of hydrogens and carbons terminated in a sulfur atom, and this is something that reacts strongly with gold. And so in these regions here, one's put these rather inert so-called alkane chains on the surface and tether them quite strongly using a sulfur atom. These can then act as a nanoscale mask, and so after an etch one can make features having used the stamp to mark the surface. B shows nanoimprint lithography in which one uses a soft coating on top of the surface to be masked, heats it and applies pressure to push the stamp in, so it's a hard stamp, and then pulls the stamp away and subsequently etches. Here's another version in which one uses a liquid on the surface, presses the stamp in, and then uses, for example, ultraviolet to cross-link the liquid and form a polymer resist on the surface, then pulls the stamp away and follows this all with an etching step. This picture here is of a field effect transistor with a 60 nanometer gate, so as good as the best technology, but made entirely by stamp technology for each step of the process. The key here, of course, being to align one stamp with the next at each step of the process. Let me tell you about a rather simple application in my lab, just to illustrate how versatile this technology is. In this case, we didn't even want to have to make a stamp. We just had a flat polydimethyl siloxane surface, and we dipped it in a chemical that had at one end a group that reacted with silicon, and at the other end a methyl group, which is a group that doesn't like water very much. This stamp was pressed down on top of a device that consisted of fluid reservoirs and then barriers etched into silicon dioxide. And the reason we wanted to stamp this surface was we wanted this part here to be hydrophobic or water repelling, while leaving the inside here hydrophilic or water loving, so it could be filled with fluid. So the stamp was just pressed down onto this to put these silane groups on the surface of the silicon dioxide with the exposed methyl groups upwards, and this prevented water from leaking around the seal that was eventually placed on the device to separate these two fluid reservoirs. Let me finish with the topic of nanojunctions. It's very often the case, particularly in molecular electronics, that one would like to make a device like this, where one metal electrode faces another metal electrode with a gap perhaps of just a nanometer or so that one could cross the two electrodes with a molecule and maybe make a molecular electronic device. Making gaps like this is extremely difficult, but one way that's been used is electromigration. The idea in electromigration is to have a waste cut in a thin gold wire so that the current density in the waste is much higher than the current density elsewhere in the device. The result is that the waste gets hotter, the atoms become more mobile and actually move with the current. So this thing blows like a fuse, but if it's made small enough and done carefully enough, the junction size can be just a few nanometers. Having said that, you can see from the images in these various panels here, taken using an electron microscope image of electromigration junctions. The scale bar here is 40 nanometers. You can see that the junctions are pretty rough and really do look as though someone has gone ahead and blown a fuse. Doug Strachan has developed a very nice solution to this problem of the sort of blowing up of nanoscale junctions by doing controlled etching of junctions. So the way this works then is the nano junction is connected into a control circuit. So let me show some current sensing resistor to measure the current passing through the junction, and then some voltage applied across the junction to drive that current. And there is a control circuit that measures this current, and once it falls below a preset value, so put some reference value in here, reduces the voltage applied to the circuit so that as the junction begins to open, the rate of opening is reduced. The consequence of this is the formation of well-shaped reproducible junctions with features, nanoscale features, that clearly align along atomic symmetry directions in the gold used for making these electrons. You can see the scale bar here is 10 nanometers, so here is a junction of approximately 2 nanometer size, and you can see clearly the orientation of these surfaces related to the symmetry directions in the underlying gold atomic structure.